All right. So we'll go ahead and take a look at the do now. So I know there's kind of a lot happening on this slide. I put the bell schedule up in the corner more so that I remember what time we finish with every class. This week, obviously, we're going to be, virtual. But hopefully next week I'll get to see some of you guys in class. So again, if you got on after, you have a couple options for a new do now sheet for this week and next week. You can print it out if you'd prefer to print the do now sheet so that you have the one that you normally pick up in class. On Google Classroom, under the Unit 5 topic, right at the top it says Unit 5 materials, do now, notes, videos, and the do now sheet is posted there. So it's a Google Doc. You can print it out. Whether you do single-sided or two-sided, remember you just need 2 weeks somehow. Or you can create your own. So whether you have a piece of notebook paper or like a piece of printer paper, just blank, you can create your own do now sheet. Basically, you just need space Monday through Friday on one side, Monday through Friday on the other. Today, we have just one do now question. And a lot of today, we're going to be reviewing what we did with kinetics before break. So to just kind of get us thinking about kinetics again. So for the single do now question for today, if a reaction is second order with respect to A and first order with respect to B, what is the rate law? And then what is the overall reaction order? So these are kind of two separate questions put into one. Could you answer one without the other? Yeah, you could. You could answer the overall reaction order part of this question without even writing the rate law. So let's look at each one because I put the answers kind of in order. So remember a rate law. So when it asks for a rate law, that's always rate equals K times the concentration of reactants raised to some power. And that power is the order. Usually we have to figure out the order on our own using that experimental data, using the initial rates. But in this case, they gave us the orders already, so they did a lot of the work for us. So what is the rate law? It's going to be rate equals K, your rate constant, times the concentration of A squared times the concentration of B. So it'll look like this. Rate equals K times the concentration of A squared times the concentration of B. Remember that rate laws only include reactants. Maybe we had another reactant C, but if they don't give us the order, that means it's zero order and it doesn't appear in the rate law. So your exponents are the orders. So then the overall reaction order is just each of the individual reactants added up. So if it's second order with respect to A, first order with respect to B, 2 plus 1 is 3. So your rate law, rate equals K times the concentration of A squared times the concentration of B, and the overall reaction order is third, right? Or we would say it's third order overall. So before we go to the next slide, I'm going to keep going back and forth between the chat. So if you have questions, comments, concerns, you can always type them in the chat. A lot of today, we're going to be reviewing what we've shown already. So this week, so again, I took a screenshot of the lesson plans. These always might change based on how things go in class. So today, we're actually going to review what we did before break. So we're going to review everything from 5.1 and 5.2. So the first part of kinetics, looking at what affects the rate of appearance, rate of disappearance. And as we go through this review, I've tried to put in some mastering questions as well. So it's kind of 2 in 1. It's reviewing and it's looking at some of the mastering questions. If you've already done that part of mastering, then you're just getting extra review. You'll notice each day, not necessarily today, but Tuesday, Wednesday, Thursday for sure, you'll see that we have examples and then time to work on mastering. Examples, time to work on mastering. So the goal is to go through examples and then use those examples that we do during class time to work on the mastering questions that go along with it. Mastering is due next Wednesday. So the 13th, that's next Wednesday at 7:30 a.m. So as of right now, you can go through number 19. So hopefully you got some of mastering done before break. And then we might have a lab at the end of the week, depending on if I can get into school. Obviously, if you see behind me, I'm teaching from home until I can come back to school. So it's dependent on if I can get into school. If I can get back into school as soon as Wednesday, I can record. If not, I might ask another teacher to record for me, or I might just push the lab back to next week. So that might change whether we do the lab or not. But all of the other like examples and mastering, that's all going to be the same. So what we're going to actually start with is we're going to start with reviewing what we covered before break. So I kind of put a little what you will need over here on this slide. So you're going to want your notes packet. So your Unit 5, I have one right here. So you're going to want your Unit 5 notes packet. A calculator would be useful. Could you use your phone? Yeah, absolutely. The math that you need to do, you should be able to do with your phone. And then I would recommend a blank piece of paper and like something to write with, because some of these questions are mastering questions. So it would be useful to have them written down. And I'm going to cover some of the material that are part of mastering questions, but it might not be an entire question. So we'll go ahead and we'll start reviewing, and you've noticed from the little picture here that it's a pair deck. So for this, you're going to notice that some slides will have you answer questions, other slides will not. So they're going to be more like content-based slides. So I tried to do both content, so I'll kind of talk through everything, and then there are some that are questions that I'll have you actually doing the math or just answering the questions in general. So once this pops up, I'll put the link in the chat. So I'll put the link for this pair deck in the chat. This is recorded, so if you need to go back and watch the recording, you can fast forward to maybe one of the mastering questions. You're like, oh, I know we did this question. You can go back and you can watch this recording. So let me go ahead and put this into the chat for you. So in the chat, I just put the link for the pair deck. Or you could just do joinpd.com and you can go ahead and you could type in the code CJBWMN. So I'll give you guys some time. There are about 8 people connected so far. And if there's a little bit of a lag, I'll like give it a second to load, because I'm now running the pair deck, Google Meet, and I'm recording the Google Meet. So it might just take a little bit of time. Okay, so we have 17 people connected. Give it just a little bit more time and then I'll start the class. If for some reason it kicks you out of the pair deck or anything, you can just go back into the chat of Google Meet and you can rejoin the pair deck, and then you should be good to go. All right, so if you ever need to rejoin, right, just use that link. So I'm going to go ahead and I'm going to hit start class. Looks like we lost a couple people. So again, If you get disconnected, you can just go to joinpd.com and you should have the little code up in the corner. So I'm just going to start by talking about rate of appearance and rate of disappearance. I actually got some remind messages over break asking if I could go back over rate of appearance and rate of disappearance, because there were some questions on this on mastering. So whether it's called rate of appearance or rate of disappearance or rate of consumption or rate of formation, those mean the same thing. When you see the terms rate of appearance and rate of disappearance, right, or consumption formation, something like that, that should immediately tell you to look at the balanced equation. Right. So as we introduced kinetics, we talked about speeds of reactions, right? How fast are reactants turning into products? Well, reactants are disappearing, products are appearing. So when we look at the rate of appearance and disappearance, we're looking at how fast are the reactants disappearing and the products appearing. Reaction rate. So when we talk about the speed of a reaction, the reaction rate is the change in products or reactants in a given amount of time. So when we're talking about the speed of a reaction, we're talking about how the reactants or products change over a given amount of time. It's just the speed. And I know that that statement right there was a question on mastering. What question? I don't remember, but I know that that was a question on mastering. Rate is the change in products or reactants in a given amount of time. So when we look at rate of appearance or disappearance, remember that we're given a balanced equation and it's always based on the coefficients. So in this graph down at the bottom of the slide, this was a question on mastering where you're looking at concentration over time. Notice how the slopes are different. The slope is the rate. So that means that A and B have different rates. So notice how A, the red line, A is appearing. You're forming more A, B is disappearing, which means A is a product, B is a reactant. But if you notice how the slopes are different, the rates are different. So A is actually forming twice as fast as B is being used up. So based on that, it could actually tell us the balanced equation. B yields 2A. B is the reactant that's being used up. A is the product that's being formed. A is forming twice as fast. And so there's a 2 for the coefficient of A. Now, the second, like kind of over on the right, you have rate equals negative change in B concentration over change in time equals 1/2. So that's another way to represent rates. We looked at that in the first video. So the biggest thing with that is notice how the rates are not the same. B has that negative to make sure that your rate value is always positive because B is disappearing. So the change will actually be negative. So there's that negative out front to make sure that rate is always positive. But B is disappearing at 1/2 the rate of A. That 1/2 could just be moved over in front of B to tell you that A is 2 times as much as B. So biggest thing is remember that rate of appearance and rate of disappearance, you have to look at the balanced equation. You have to look at the coefficients. So if we look, let's practice with this one, right? This is, put up in the corner, this is similar to number 7 of mastering. So consider the combustion of H2 gas, and I give you the balanced equation. If hydrogen is burning at the rate of 0.48 moles per second, what is the rate of consumption of oxygen? So you have the balanced equation. If hydrogen is burning, so H2's rate is 0.48 moles per second, what is the rate of consumption of oxygen? And what we're going to do with some of these practice problems is I'll let you guys answer, and then we'll actually look at the work for it. All right, and this is similar to number 7 of mastering. So if you haven't done mastering yet, or maybe you skipped through mastering, You can kind of make yourself a note. So hydrogen is burning at the rate of 0.48 moles per second. What is the rate of consumption of oxygen? Remember, so when it says rate of consumption, that is rate of appearance, rate of disappearance. That tells you should be looking at the balanced equation. Okay, so we have about 19 responses. And for this, I know this was a multiple choice question, but it was just to make it a little bit easier to see. So most of the responses, let me show. Right, so most of the responses was 0.24 moles per second. But we had some people choose 0.48 and some choose 0.96. So let's look at this problem. So if hydrogen is burning at a rate of 0.48 moles per second, so what I did is I worked through this on a whiteboard and then I just put a picture of it on the slide. So they gave us the balanced equation. Start with the rate that they give you, 0.48 moles per second. And then over here, I just put of H2. Then you can use the balanced equation, use the coefficients to go from one substance to another. I didn't even put moles or anything in front. I just did H2 and O2. So 0.48 moles of H2, but for every 2 H2, you use only 1 O2. So 0.48 moles of H2 divided by 2 is 0.24 moles per second. So we can notice how oxygen's coefficient in the balanced equation is a 1. It's half that of H2. So its rate is also half that of H2. Again, it says what is the rate of consumption of oxygen. So oxygen is consumed because it's a reactant. When you are giving answers for rates, the value of rate is always positive. So a rate is always a positive number, but it's being consumed because it's a reactant. Okay, so let's try one more. So again, same balanced equation, same rate even. Hydrogen is burning at the rate of 0.48 moles per second. What is the rate of formation of water vapor? Yeah, there's a lot of people choosing the answer already, maybe without even doing any math. So you can set this up just like we did before. You're starting with hydrogen. Its rate is 0.48 moles per second. I want to know the rate of formation of water vapor. Okay, we have all the responses. We take a look. A majority chose 0.48. Let's look at the work for this. All right, let's look and see if 0.48 is the correct answer. So if hydrogen is burning at 0.48 moles per second, we can look at the balanced equation, rate of formation. So when you see words like rate of consumption, rate of formation, rate of appearance, rate of disappearance, that tells you that you need to be looking at the coefficients. So 0.48 moles per second of H2, for every 2 H2, you produce 2 H2O. Or you can just look at the coefficients and say, well, the coefficients are the same. If the coefficients are the same, the rate of appearance and the rate of disappearance are the same. But H2O is being formed since it's a product. Again, rates should always be given as positive values. Okay, so that's looking at a question from mastering. So whether your numbers might be a little bit different, but it's still very same idea. Right, so that's number 7 of mastering. Remember, you can always come back to this recording later if needed. So how is reaction rate related to concentration? So there are different factors that affect the rate of a reaction. So we talked about different factors that affect the rate of a chemical reaction. You can change the concentration of reactants. So here is where we focus in on reactants. The reaction rate, to calculate rate, you can look at the change in reactant concentration or the change in product concentration over time. But when we're looking at what affects the rate itself, we're looking at how the concentration of reactants changes. You can look at adding a catalyst, more on a catalyst at the end of the week. You can increase temperature, and you can change the physical state of the reactant. So we talked about increasing surface area, going from a cube, right, or a block of salt to grains of salt. Something to always keep in mind is that anything that increases the collisions between the reactant particles will increase the rate. So our justifications for why increasing concentration increases rate, our justification has to be that when we increase concentration, we're increasing the number of particles and we're increasing the collisions. Everything has to come back to the collisions between the reactant particles. Then we also talked about rate laws. So a rate law mathematically describes how the rate depends on the concentration of reactants. So a rate law is written, and we did this in the do now, rate equals K times the concentration of reactants to some power. And this power is the order. Might be 0, 1, 2, or 3. You could technically have fractions. We don't see that as often. Usually we see 0, 1, or 2.
I'm not sure I understand.
Ooh. But this information, this is the rate law, right? You always have to have rate equals K and then your concentration of reactants. Now, if all of your reactants are 0 order, then your rate law is just rate equals K. So you always have to at least have rate equals K. Remember that your rate constant, K, only changes if temperature changes. Otherwise, it is a constant. So, and some different ways to talk about the order of a reactant. So you could see it written as order with respect to A. It might say it's first order in A. Those mean the same thing. I try to show you different terminology because College Board will use different terminology as well. So we also, when we looked at reaction orders, we used the method of initial rates, and we'll look at some of those in a little bit, where we look at if this doubles and this doubles, it's first order. If this doubles and this quadruples, it's second order, so on. But there's this table at the top that summarizes you have to determine reaction orders experimentally. Okay, I'll say that again. You have to determine reaction orders experimentally. They are not the coefficients in a balanced equation. Right? They are not coefficients. So now, are there times like in the do now when they tell us the order already? Yeah. But if you are not told the order, you have to figure it out based on data. So let's look at this question, and some people are already answering. A reaction A plus B yields C obeys the following rate law. Rate equals K times the concentration of B squared. If the concentration of A is doubled, how will the rate change? All right, so read that carefully. All right, I'm going to read it again. I want you to listen carefully. This reaction, A plus B yields C, so your reactants are A and B, obeys the rate law, rate equals K times the concentration of B squared. If the concentration of A is doubled, how will the rate change? So look at the rate law and look at the reactant that you're changing. So we have about 18 responses so far. And there are questions similar to this on mastering. I was using mastering as I was making these questions. I know this looks very similar to the one we did when we reviewed for the quiz, but the questions are different. Okay, so let's take a look at the responses here. And we have a few different answer choices. So at least we know that B was not correct, right? We're not cutting anything in half. So we had some people say the rate will be quadrupled, some say it will be doubled, and then 13 people said it would remain the same. So here's what I want you to focus on. The rate law only has B in it. A is nowhere to be found in the rate law. A is a reactant, but it's not in the rate law, which means I see more people changing their answers, right? If A is not in the rate law, it's zero order, which means if A is not in the rate law, you can change that as much as you want. A is not going to affect the rate. So the correct answer is that the rate would remain the same because A is not in the rate law. So changing the concentration will not do anything to the rate. It's a zero order reactant. Okay, good. So here's that same rate law that we just looked at. Rate equals K times the concentration of B squared. So I want to know what is the order with respect to A, what is the order with respect to B, and what is the overall reaction order. So you can drag the numbers to each of the questions. You might not use all of the numbers. I just tried to put different numbers there for you. But I want to know what is the order with respect to A, order with respect to B, and the overall reaction order. So remember that A, notice on the balanced equation, A is still a reactant. We just don't see it in the rate law. And again, this is there is a question just like this on mastering. It's going to be somewhere in the 5.2 section, but I was just pulling from different questions. So if we look at the responses, right? So notice we have 0, 2, and 2. Good. So A is zero order, right? A is not in the rate law. So even though it's a reactant, it's not in the rate law. That means it's zero order. That's why doing anything we want to A will not affect the rate. B is second order. The exponent tells us the order, and then the overall is when you add them up. Good. So again, use the rate law to figure out orders. So again, going along with reaction orders, you'll notice up at the top, this is mastering number 13. So I gave you that table again that was on the slide before. Consider a hypothetical reaction between A, B, and C that is first order in A, zero order in B, and second order in C. What's the rate law? Oh man, I didn't change this. Okay, 1 second. We're not going to choose an option here. So these, I must have, okay, here. I'll tell you what the rate law is. Okay, so don't worry about answering this because this doesn't even make sense. But try to write the rate law down, right, on your piece of paper. If it's first order in A, zero order in B, and second order in C, what is the rate law for this? Again, you don't need to answer it on the multiple choice because it doesn't make sense. Make myself a note that this needs to be fixed. So I'm just going to talk through what the rate law should be. You can check what you have written down. So your rate law will be rate equals K. Don't ever forget that K. So rate equals K times the concentration of A times the concentration of C squared. And so again, rate equals K. So you have rate equals K times the concentration of A. Now, if you want to put A to the first power, you can, but it's first order. It's zero order in B, which means B is not in the rate law at all. And it's second order in C, So it's going to be concentration of C squared. So rate equals K times the concentration of A times the concentration of C squared. You're going to need that rate law for the next couple of questions. So again, rate equals K times the concentration of A times the concentration of C squared. All right, now, here we go. So consider this reaction, right? And I just said if the rate law is rate equals K times the concentration of A times the concentration of C squared, how does the rate change when the concentration of A is doubled and the other reactant concentrations are held constant? So focus in just on A. If the concentration of A is doubled and all the other reactant concentrations are held constant, what would happen to the rate? If you're focusing just on A. Good. We have 12 responses and they're all the same response so far. Good. All right, so I want to know how the rate changes when the concentration of A is doubled and the other concentrations are held constant. So that means if everything else is held constant, C is not going to matter, B is not going to matter because they're being held constant. You're focusing just on A. So let's take a look at the responses. The majority said that the rate would be doubled. What I want you to focus on is the rate law, right? The rate doubling is the correct answer here. If A, so when it says that A is doubled and everything else is held constant, that means that you need to focus in just on A. A is first order. So whatever you do to A, you do to the rate. So if you're doubling the concentration, you're doubling the rate because C is constant and B is constant. Good. All right, so now it's the same rate law, same reaction, but now I want to know, how does the rate change when the concentration of C is tripled and the other reactant concentrations are held constant? So everything else is held constant. So A and B are held constant. So you're zooming in just on C. Focus just on C. If you triple the concentration of C, what's going to happen to the rate? Okay, so let's look at the responses here. So we have two different answer choices. Some said that the rate would be tripled. Some said the rate would be multiplied by 9. So let's take a look at this rate law. Right, so we're focusing just on C. A and B are held constant. It tells us that. So focus just on C. C is second order. So what that means is whatever you do to the concentration, you square that, and that's what you do to the rate. So notice in this table, it says as A is doubled, rate quadruples, right? In this table, if it's second order, you double it, multiply by 2, 2 squared is 4, so the rate quadruples. So we're not doubling, right? We're tripling in this case. So if the concentration of C is tripled, that means you're multiplying by 3. 3 squared is 9. So if you are tripling the concentration of a second order reactant, you are going to increase the rate 9 times. So the correct answer for this is C. The rate would be multiplied by 9. All right, so here's a bit of a challenge question, right? So it's, again, the same reaction, but now I said, how would the rate change if all three reactants are tripled. If all three reactants are tripled, how would the rate change? There's a question similar to this on the quiz, but it wasn't tripling. I gave you what was happening. And I'll give you a hint. If you're looking at this and you're like, I have no idea, plug in a 3 into each reactant concentration. Plug in a 3 to each reactant concentration and see what number you get. And I know that you're going to have something times K. That's fine. K is a constant. But just look for what number you get, because that's the factor by which the rate will change. Yeah, I see some people are doing that and they're changing their answers. Good. So again, when you have questions like this, so as some people are finishing up, maybe doing the math, as you are doing questions like this and you're changing multiple reactants at the same time, do what I just said. Plug what you're doing to the reactant in for the reactant concentration. So if we look at our responses, right, majority of people chose B. The rate would be multiplied by 27. That's correct, right? The rate would be multiplied by 27 because plug in a 3 in the rate law. Plug in a 3 for the concentration of A and a 3 for the concentration of C, because you're tripling. So you're multiplying by 3. Well, 3 squared is 9. 9 times 3 is 27. Right? So again, that is also, right, this was all part of number 13 of mastering. So this is looking at number 17 from mastering. So the iodide ion reacts with hypochlorite, and they give you the balanced equation, and then they give us data here. So they give us trial 1, trial 2, and trial 3. So remember, to determine the rate law, we have to use the method of initial rates using experimental data. So what that means is you have multiple trials, multiple reactions that you have to use. We can determine the order of each reactant, right? The order of reaction for OCl minus means what's the order of OCl minus? The order of reaction for I minus, what's the order of I minus? And remember, when you're looking at this, and I see some people are typing in their rate law, remember that you want to look at how one reactant changes while the other remains constant. And look and see, what does that do to the rate? What happens when you change one concentration? What does that do to the rate? So I want to know, using that information, what is the experimental rate law? All right, and you can actually plug in, you know, OCl minus, I minus. If it's easier just to use variables, you can as well. So as some people are still typing, if we take a look at the data here. So let's look at how OCl minus changes and I minus stays constant. So that's between the first and the second trial. OCl minus doubles. It goes from 1.5 to 3 times 10 to the negative third. So when OCl minus doubles, the rate doubles. That's first order. So OCl minus is first order. Then look at how I minus changes. So I minus changes from trials 1 to 3 as OCl minus stays constant. And so from 1 to 3, I minus doubles, the rate also doubles. So that means that I minus is also first order. So I was just looking at some as they were, being typed up. So notice rate equals K. Don't forget K. Check your rate law. If you do not have the rate constant in your rate law, make sure that you add that. So rate equals K times the concentration of OCl minus times the concentration of I minus. Right? So they're both first order. They're both first order because as the concentration doubles, the rate also doubles. So this is what is called the method of initial rates, determining the order of each reactant experimentally. Okay, so remember with the rate constant is K, and it's a constant as long as we're at the same temperature. So typically you're going to see a lot of these are going to say at 25 degrees Celsius. So these reactions are at 25 degrees Celsius. That means that K is constant. Now, once we have a rate law, remember that we can calculate K. We can plug in one of the sets of data into the rate law and we can solve for K. Now, you need to make sure that you know the units. So whether you want to plug in your units and work it out every time, or you want to just memorize this table, that's up to you, but you need to make sure that you know units. Notice that the units for the rate constant are based on the overall reaction order. So whether it's first order overall or second order overall, because you're actually plugging in molar per second for rate and molarity for concentration. So it's based on how many reactants you have. So let's go back to number 17 of mastering. And remember that your rate law was rate equals K times the concentration of OCl minus times the concentration of I minus. And I want you to calculate K and include units. All right, so calculate K and include units. Get my calculator for this as well. And you can pick any of the trials. So you can pick trial 1, trial 2, trial 3. The one you pick is up to you. You're going to get about the same answer every time. Good. I see a lot of people starting to type in the numeric portion. So whichever trial you pick doesn't matter because it's a constant. So will it vary a little bit based on sig figs? Sure. But for the most part, if you round to 3 sig figs, you should be getting about the same answer every time. Okay, so I notice a lot of people, right, are giving answers. Now, I'm going to go through, I'll talk through the rate constant. And I noticed that some people, even they're not sure what the value is, but they put the units. And that is a great strategy. So if you're not sure of what the actual value is, but you know that the units should be something like, you know what the units should be, that will probably give you at least some of the points. So I'm going to talk through while some people are still calculating, because I noticed that for the most part, everyone has a similar value, but there are a couple values that are a little different. So here's what I want you to do. Make sure you have your rate law written down. So your rate law is rate equals K times the concentration of OCl minus times the concentration of I minus. I just picked the first trial to plug in. So rate is 1.36 times 10 to the negative fourth. Right? Rate is 1.36 times 10 to the negative fourth. That equals K times the concentration of OCl minus times the concentration of I minus. So you have 1.36 times 10 to the negative fourth equals K times 1.5 times 10 to the negative third times 1.5 times 10 to the negative third. And so what you're going to do, and you have to be careful with your order of operations. I did 1.36 times 10 to the negative fourth divided by the quantity 1.5 e negative 3 times 1.5 e negative 3. The value that you should get is 60.4. Or if you have 60.44, that's okay. Right? So whether it's 60.4 or even 60, 60.44, that's the value, the numeric value of K that you should get when you plug everything in. Now, when you plug in your units with that, you're going to have molar per second divided by molarity squared. This is a second order overall rate law. Each reactant is first order, so overall it's second order. Your units are m to the minus 1, s to the minus 1. So 60.4 m to the minus 1, s to the minus 1. Because it's second order overall. If you plug in units, right, if you plug in units, you will have molar per second divided by molarity squared. The molarity on the top cancels with one of the molarities on the bottom. To the minus 1 means it's in the denominator. So that means it's 1 over. So like m to the minus 1, s to the minus 1 is the same as 1 over m times s. Okay, so that's looking at calculating K. We have one more slide where we're going to try to kind of put everything together. So for this, I gave you some data from 3 experiments. What is the experimental rate law for the reaction? And then calculate the rate constant with units. So the first thing I want you to do, and you'll do this in the same box, what is the experimental rate law? Right. I see a lot of people before they even realize what the orders are, they're typing rate equals K. It's a very good strategy to have when you're doing rate laws, right? Rate equals K, and then you can figure out your order. So take just a little bit, figure out the order of each reactant, write the rate law, and then calculate the rate constant with units. Okay, so I see a lot of people's rate laws, and some people's are different than others. So I'm going to give you a little hint. Remember when you're looking at, for example, NO, you need to look at where NO changes, but O2 remains constant. So when you're looking at where NO changes, you should be looking at experiments 1 and 3. All right, experiment 1 to 3 for NO, because NO changes, but O2 stays constant. So from experiment 1 to experiment 3, NO doubles and the rate quadruples. So I'll say that again. From experiment 1 to 3, NO concentration doubles, the rate quadruples. Because if you do 0.0252 divided by 0.0126, that's 2. If you do 5.64 e negative 2 divided by 1.41 e negative 2, that's 4. So when NO doubles, rate quadruples. That's second order. So NO is second order. Here's your tip for oxygen. You don't have to look from, 1 to 2 or from 2 to 3. For oxygen, I looked from experiment 3 up to experiment 2. So I looked from 3 up to 2. NO stays constant, but O2 from experiment 3 to experiment 2, O2 doubles, and the rate also doubles. So that's first order. So again, if you check your rate law, NO is second order, O2 is first order. Then based on that, calculate K. So again, for your rate law, NO is second order, O2 is first order. Then you can pick one of the trials. It doesn't matter which trial you pick. Pick one of the trials and plug everything in to solve for K. And don't forget about your exponents. I got a big number for K. Looks like other people also got relatively large number. By a big number, I mean like 7,000 and something. Yeah, so I got, and it looks like a lot of people had something similar. So let me pick a couple just so I can put them up on the screen. All right, so I'm going to put a few of the responses up here on the screen. So your rate law, right? We talked through the rate law already. Again, your rate law is rate equals K times the concentration of NO squared times the concentration of O2. Then when you're plugging everything in, you can pick any of the trials, right? I picked trial 1 because it was at the top. But you pick any of the trials and you plug it in. But don't forget about the exponents. NO is second order, so it's squared. And so when you plug in your concentration of NO, make sure that you're squaring that. Notice for the rate constant. Right, so these three responses had 7105. If mastering wanted 3 sig figs, it would be 7110. Just keeping that in mind. But notice how they're all m to the minus 2, s to the minus 1. Remember that it's always s to the minus 1. What changes is the m. So m to the minus 2, s to the minus 1, because this is third order overall. So since it's third order overall, you're going to have m to the minus 2, s to the minus 1, because you're going to have molar per second divided by molarity cubed when you're rearranging your equation. And so you're going to get 7105, or if you round to 3 sig figs, 7110, m to the minus 2, s to the minus 1. Right? And again, that is, I can't remember what number it is on, that's like 18, I think, on mastering. So very similar to mastering as well. So I'm going to go ahead and I'm going to end the practice. And then we're going to look at just kind of what to do for second period. I know we kind of went into second period, but hopefully this was useful. I'll definitely go over any questions that there might be, kind of after we go through. So again, if you need to go back and review any of the slides, any of the practice, it is all recorded. I'll post it. I'll put the Pear Deck slides. I'll put it under the Unit 5 materials, and I'll put it in or on the class website. So all these different Pear Decks that we're doing, so you can at least see the questions. So for the rest of class, what I want you to do first is we're going to move ahead to video 5.3. So you'll notice it's been up in Google Classroom for a few days, but I want to give you time in class to watch it. So you're going to watch video 5.3 in Edpuzzle, take notes. You want that done for tomorrow. You'll notice it's due at 7:30. Then once you watch video 5.3, then you can go back, work on mastering. So still at this point, you can go up through number 19. Remember to pay attention to those that are extra credit versus points versus practice, because the practice is worth 0 points. And I put a screenshot up here just so that you can see, right? Number 1 was extra credit, but number 2 was practice. So it says it there, but then it also, has the tutorial and says whether it's extra credit or whether it's practice. So again, watch video 5.3 first. You should be able to get that done before the end of second period. Tomorrow, we're going to be going through the examples for video 3. So I want to make sure that you have that done. And then you can work on mastering. So the only thing in terms of, quote, homework for tomorrow is to make sure that you have that video watched. So you might as well do it now, right, while I'm giving you time, like during class, to watch it. And so